Next, we want to practice going from exponential form to logarithmic form. So in the previous example, we went from logarithmic form to exponential form. In this example, we're going to go from exponential form to logarithmic form. So you need to be able to go back and forth between the two. So the base of the exponent is always the base of the logarithm. So this is going to be log base 2 of 16 equals 4, because remember, the logarithm is the exponent. In this case, our exponent is 4. So the logarithm is going to be equal to that 4. In this case, we have the base is 9. The logarithm is equal to the exponent, which is 3/2. And so this is where the 27 goes, and this is where the 3/2 goes. And for this next one, I would begin by writing log and then the base. If we think of this as our exponent right here, then our base is a. And so we get log base a. And then our exponent is -2. And 1 over a to the second power is the argument. And similarly here, this right here is my base. This right here is my exponent. So I fill in log base 5 of my argument is equal to the exponent. So you need to be able to go back and forth between these two forms very smoothly, because you can often use one of the two forms to answer various questions. In the next part, we want to evaluate the logarithmic functions at the requested input. So we're going to replace x with this, and then we're going to ask the logarithmic question in order to find the result. So for the first one, we have f of 32, which is equal to log base 2 of 32. And the question this is really asking is, what power do I need to bring 2 up to that power in order to get 32? And I know that 2 to the 5th power is equal to 32. So the exponent is 5. For this one, I have f of 1 equals log base 7 of 1. And so therefore, I ask, what power do I need to raise 7 to in order to get the result 1? Well, that's really like asking the question, and I'm going to write the question out this time. This is really just happening in my head, though. You don't have to write this out. I'm thinking 7 to this power has to equal 1. So the thing that's going to work here is 0. So the exponent is 0. Similarly, for the previous one, the question I asked in my mind was 2 to this power equals 32. And so the answer is that the power I needed was 5. Okay, let's go on to the next question. I now have f of 1/1000th, which means that I'm actually finding f of 10 to the -3. And if you didn't really practice in the last section your rules of exponents that allow you to rewrite fractions, or change between negative exponents and fractional form, or practice your common powers, this is where it really starts to pay off. You want to be able to effortlessly recognize that 1/1000th is exactly the same as 10 to the -3. So when I plug that into my function, I have log base 10 of 1/1000th, which is the same thing as 10 to the -3. So that asks the question, 10 to this power should equal 10 to the -3. And the answer to that question is that the exponent I need is -3. And next up, we've got f of 5 is log base 125 of 5. And that asks the question, 125 to this power is equal to 5. And the mistake I often see for this one is that people will give me 3 because they see 5 to the third power is 125. That relationship plays a role here, but remember that what's actually happening here is that I'm taking 125 to the 1/3 power, which accomplishes cube root of 125, which gives me the result I need. So it's not that we're using that 5 to the third power is 125. The exponent we need is the exponent on the 125. So that exponent that we need is actually 1/3. So this takes a little bit of practice. It may take a little review of common powers. I don't necessarily expect you to have memorized 5 to the 8th power, but probably 5 to the 2nd, 3rd, 4th power. A lot of the beginning powers for some of our smaller numbers are important to have memorized. And similarly, being able to connect that to roots, to go forward and backward between exponents and roots, being comfortable with fractional exponents, and being comfortable with negative exponents. It all plays a role here. And if you're having trouble, you can ask your instructor, which if you're in my class, you can ask me for resources on how to review those concepts. We're going to finish off this page with a definition. The logarithmic function where the base is 10, instead of something like 2, 7, or 125, the one that's specifically base 10, is called the common logarithm. And we like it because our number system is base 10, so it can be useful to us. It's denoted by log base 10, or if I simply write log with nothing written next to it, like if I write log of 1,000, then that means, here, let me move this up into this space so you can see that I am not answering that question right there. Log of 1,000 means log base 10 of 1,000. So I'd be able to say that log of 1,000 is 3 because 10 to the third is 1,000. So if we want to come up with a rough estimate for log of 200, a very rough estimate, we could find by looking at what are some powers of 10. So remember, 10 squared is 100. 10 cubed is 1,000. So it's going to be somewhere in between there because 200 is between 100 and 1,000. So therefore, log of 200, which is the same as log base 10 of 200, well, the power I have to raise 10 to in order to get 200 is going to be between 2 and 3. So it's going to be a little bit bigger than 2. And you can type that into your calculator using the log button in order to work with this. You're going to notice that your calculator does not have any other buttons besides log and something we're going to talk about in a second, which is ln, which stands for natural log. Okay, we're finished with this page. We're going to take a look at some of these just plain old log, aka common log functions, and then generalize some properties.